I hope I'm on. Good morning. Good morning. And now I will review very shortly, but next time I will give you a more full review of what is left in our course. So that is lecture number 20. And okay, syllabus contains the following topics. 1, deflection of beams. That we covered very beautifully. Then, statically indeterminate beams. That was also covered totally. Then, static failure criteria. Then, energy methods. And then 5, instability or buckling. Buckling of columns. So that was also covered. So we are left with 2 topics. These 3 topics 1, 2, and 5 are heavy topics from the point of view of scope. So each needed approximately 3 weeks to 1 month. These 2 topics are smaller relatively, so the topics 3 and 4 will be covered in April. Okay, now topic 3, static failure criteria. Is not covered in the book. In the textbook by Hibler. Ninth edition. Because it is considered because this topic is somewhat advanced. That is why it belongs to intermediate strengths. So I'm giving you my own exposition of these topics, of this topic. Okay, then what is left actually is we are left with 1 test, 1 more project, and 1 retake test. I think I gave date of this one. Date was given. That is a date where so-called final exam is scheduled. We have no final exam. However, during that time, we will administer retake test where student can retake one test that he or she wants to improve. Okay? As you know, each test is 20% of the grade, so two tests, 20% plus 20%, and projects 10% plus 10% plus 10%. That is designed specially that you first learn the material. So learn the material. And plus, and that was my personal consideration, reduce effects of tests because they are in confined time span, and may cause to anxiety, pressure, etc. So in order to take this pressure from your lives, I actually offer projects which are also making you closer to your reality, so to say. Now, today is April 2, I think. The best advice I can give you: no outside work if you can afford. In April. Totally dedicate to studies and success in them. Okay, that is usually, I give such a recommendation 2 times a year. One is November 1 for fall semester, and April 1 or 2, in this case 2, during spring semester. Please, this recommendation naturally is a very good recommendation. I'm told by students that may save the semester. And I'm sharing with this recommendation to you, which is applicable not only to this course, but to any other course and any other semester. So 22, static failure theories. So that is how it says in the syllabus. Okay, what is the simplest possible case? Simplest possible case we already know. You know both in Strengths of Materials 1 or first course, regular course. So we are subjecting a beam or a bar, so that is a bar or a rod, to an tension, stress in positive stress. So that is the simplest possible case, uniaxial tension. So what we do is take a specimen, subject it to some load P, then there is initial cross-sectional area. So we divide P by cross-sectional area because of so-called Saint-Venant's principle. Saint-Venant was a French engineer. He says, far away from load application, okay, or cross-sectional change. Location, okay, load application location, sorry. Or cross-sectional change, stresses are uniformly distributed. So that is a true distribution under the load. But far away, say here, then far away from the application of the load, Seminon says, stresses are uniformly distributed, that is sigma, and that is P over A sub 0. Okay, then we increase the load. We increase the load, and it turns out that this is a linear line, straight line. First, this diagram, and then we have sigma versus epsilon. We are measuring new lengths minus original lengths divided by original lengths. That is deformation or strain. So it turns out that the linear relationship holds until something that is called sigma PR, proportionality, not public relations, but proportionality limit. According to the Hooke's law, in this region we have Hooke's law is valid. Sigma and epsilon are proportional to each other. Okay. So actually Hooke said that deformations as tensions. That was his phrase. Can you imagine just this one phrase, okay? 3 words made him famous. He actually allowed strengths of materials, theory of elasticity, theory of plasticity, and design in mechanical engineering, ocean engineering, aerospace engineering, automotive engineering to take place. So sigma is proportional to epsilon. Now this coefficient of proportionality is E, we denote by E. Okay, E is proportionality constant, modulus of elasticity, or Young's modulus, after Thomas Young, who introduced it. So then, next one here, there is something before it turns, okay, before there is inflection point and going to sigma yield street. There is sigma E. Elasticity limit. Now, what is elasticity limit? That is sigma elasticity. So that is a bit to the right. If we are unloading, we are going by the same line. If we are unloading from, that is proportionality limit, sigma proportionality. After that is not proportional, that is already nonlinear behavior. But still, in the beginning, if we unload, then we go back by the same line. However, if we cross a bit, so this guy is sigma bigger than sigma E, then we are not going according to the original loading line, but some line which is parallel to this line. Okay, that means that, okay. Now, behavior after sigma E, beyond sigma E, material is not elastic, but there is a plasticity effect. Plasticity is lack of elasticity. Okay, this yield stress is a dangerous position. We are told, for example, in some stores now, so there is a, say, cashier, and then there is a shield, okay? That is a shield. Shield was introduced. So this shield says that sigma should be not just smaller than, sigma stress should be smaller than yield stress. That is a design consideration. It should be actually smaller or equal than sigma allowable. This sigma allowable lies below sigma. So that is the shield or buffer zone. Okay, or protection distance. So sigma allowable equals sigma yield divided by K required. K required is required safety factor. This was introduced for the first time by Belidor, 1729, French engineer. He said, without justification, but he said he was building some church in Paris, and he said that K required, he took equals 2.3. Okay. Anyways, K required should be bigger than 1. Otherwise, we don't have the protection, or otherwise we don't have a shield. Okay? Must be bigger than unity. Sigma allowable is a fraction of sigma y. That is some fraction. Proper fraction. Okay, now we are asking many questions, of course. That is what we are good at, to ask questions. We humans are asking questions. What happens, namely, when does element break? If there is no uniaxial stress. Okay, uniaxial stress we know. We learned it in material science. We learned it in strength of materials in the first course. What happens, namely, multi-axial stress state? What happens in the multi-axial stress state? What is this? So look, this is uniaxial. Now what happens if there is a load here acting like this? Okay, there is additional stress, say in outside direction. Okay, then what we can do is what we could do. That is my explanation. I never read in any book this explanation. Okay, what we can do is then, pay attention, conduct new experiment, but here will be 1 kilonewton. And we keep this 1 kilonewton constant. Then we increase the load, and we will find when it will be broken. So probably this value will be less than here, so probably behavior will be like this. So we have to find this experimentally, it's smaller than yield stress. Then we imagine that there are 2 kilonewtons. Then we will find, we again do the experiments here, and we will find this value, which is smaller than this value. Then we continue this, 3 kilonewtons, 4 kilonewtons, etc. So what we can do is as follows. Look, please, create a table. So this value we know already from every book. Then we have to have a table which contains the following data. If there is 1 kilonewton, then the breaking stress is this. If there are 2 kilonewtons, then breaking stress is this, etc. So what we are doing, imagine we need 10 power in 6 or million different values of lateral stress. Okay, this 1 Newton, then 2, then 3, then 1 million, imagine. So then pay attention. What we have is as follows. That is a dangerous stresses. Sigma yield if we have 0 in lateral. Sigma in lateral direction is 0. Then that is sigma yield. Then if there is 1 kilonewton, then some value 1. If there are 2 kilonewtons, then some value 2, which is smaller than value 1. Then if 3 kilonewtons, then it's value 3, which is smaller than value 2 and smaller than value 1, etc. 4 kilonewtons, etc., 10 in power 6. Okay, okay, that is fine. So what we can do is then have this, we can publish these results. Say in a book. So if every page has 20 entries, then how many pages we will have? 10 in power 6 divided by 20, or 100 times 10 in power 4 divided by 20. That equals 50,000 pages. Okay, so such a book will have 50,000 pages, or maybe will be 50 books, each 1,000 pages. Okay, then we are continuing. But what happens if there is a stress in the third direction? What about stress in third direction? Then we can do the following. Look, please. First of all, we can conduct this experiment when lateral stress is 0. Then lateral stress is 1. Okay, that second entry. Then we keep this lateral stress 1 and increase. So here this is 1, and then it is 2. So then this is 1, then it is 3, etc. So whatever experiment we did before, we are doing with 1. Then we are doing with 2 here, and etc. For each value sigma z equals 1, say 10 in power 6 cases of sigma y. We increase sigma x and get experimental failure value. Number of values for sigma z, 10 in power 6, imagine. So total will be 10 in power 6 times 10 in power 6 experiments. Okay, as I said, we should put it into a book. So let us calculate number of pages of these books. So will be 10 in power 6 times 10 in power 6 divided by 20 lines per page. So 10 in power 12 divided by 20. So it's 100 divided by 20, 10 in power 10. So it is 5 times 10 in power 10 pages. Too heavy a book. Maybe we could put it on World Wide Web. That is also a possibility. But it's very expensive set, but there is very expensive set of experiments. Anyways, humankind did not go this way. The way that I described to you, humans did not go. Humankind decided differently. Okay, what is it differently? To develop static failure theories. So to develop some theories. Some theories about collapse. Because experimental way is too expensive. We could have done, maybe experiments could have succeeded. For example, maybe United Nations could have decided that, so to say, so many experiments are conducted in the United States, so many in China, so many in Russia, so many in various countries, and then put it on World Wide Web. Anyways, this was not done. So this is what we have in syllabus, this term. But this term, the term static failure theories, is unsuccessful. Why it is unsuccessful? Because that is not a theory actually, but a compatibility with experiments. We are checking compatibility of our assumptions, so we are doing some assumptions. And then we are checking with experiments, and so, but that is not a theory. Better term will be static failure criteria. So I will teach you the static failure criteria. Okay? If you want, that is like models. By the way, if you know, there are several coronavirus propagation models. Okay, I hope that reality is much better for us for all of us than these models. Okay, so how these criteria work? Pay attention. We have this multi-axial stress. Multi-axial stress. Multi-axial stress state. This we know how to deal with this. That we know, uniaxial state. So criterion will be, look please, criterion will, so here we have three stresses, sigma 1, sigma 2, sigma 3. How do I denote the stresses? Sigma 1 is the biggest. Or largest. That is smallest. Intermediate one is sigma 2. So sigma 1 is greater than sigma 2, greater than sigma 3. I should have written sigma greater or equal. Sigma 2 greater or equal, because sometimes the stress, some of the stresses could be equal to each other. That is a general stress state. Now we should say criterion, we should suggest some criterion which will make this state equivalent to this state. What does that mean? That means that equivalence, so that is this equivalence. Okay? We should multiply stresses in multi-axial stress by the same number as we should multiply sigma equivalent, this state, uniaxial stress. To get a failure. That means that this state and this state are equally far away from failure. We have to multiply this condition proportionally. by the same number as this. So from failure point of view, this and this are equivalent. Here there is a criterion. Okay, the question is, what is this criterion? We will discuss it. Now, then there is a third step. So that is step 1 is a criterion. That is step 2. Step 2, we comparison. We are comparing with sigma yield here. Then we should say sigma equivalent should be smaller than sigma yield. Okay, so I will write it down here. Sigma equivalent should equal smaller or equal than sigma allowable, which equals sigma yield divided by safety factor, K required. Any questions here? Please, 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 by all means, send me questions. When you are sending a question, say about some page, write down page 2010. But please don't send me like this. I have a question on 2010. Please explain it. Because in order to explain an entire page, I have to cover a lot of time. Okay? But you can ask, what is written there in this box underneath step 1? Why did we need this criterion? Because without any criterion, we don't know how this relates to this. Can we reduce this situation to the situations that we know? Okay, that is a very mathematical approach. Reduce what you know, reduce what you don't know to what you know. Okay? Indeed, this situation we know. If there is uniaxial condition, then we know, we learn it in many subjects. First criterion. First criterion is, look please, it's called maximum normal stress criterion. So maximum stress is what defines the situation. So maximum stress here. So these two conditions, so we will say two conditions, multiaxial and uniaxial, are equivalent if they share maximum normal stress. Okay? So here maximum stress is sigma 1. Because maximum of sigma 1, sigma 2, sigma 3 is sigma 1. Here maximum stress is, look, here there is sigma equals 0. And this sigma equals 0 also. So maximum sigma equals sigma equivalent. So maximum sigma equals sigma, maximum between sigma equivalent 0, 0. That equals sigma equivalent. Now we say that sigma equivalent equals sigma 1, and that should be smaller than yield stress divided by K required. Okay? That is the first criterion. First criterion is a criterion that first comes to mind. Because maximum, surely that maximum stress should play some role. Let me write it down. Surely maximum sigma should play some role. But this criterion says it plays 0. Okay, that is a main player. Okay, pros. What are the pros of this? I'm asking you also, you are sitting now in your room and you are thinking, what are the pros? Means what suggests that this is correct? Okay, maximum stress should be playing some role, naturally. That is one of the possibilities. Second, okay, think about second and communicate to me. What is a pro of this approach? Cons. Okay, according to this criterion, sigma 2 and sigma 3 do not play a role, are unimportant. Okay? Like, if someone thinks that in an organization only CEO is important, then that person also thinks that others are not important. Is it right? So according to this criterion, imagine we have this 1,000 kilonewtons, 999, 998. Or 1,000, 1, 1. Or 1,000, 1, 0. All these conditions are the same from this failure criterion mode. Okay? All these states, according to this criterion, are equivalent. But we should think that this cannot be, because this condition probably is more dangerous than this condition. Okay? A is more dangerous. Than B or C. Anyways, if you are coming to the organization where maybe experiments show that maximum normal stress criterion should be used, then you will use that criterion. Because you, as an engineer, you are following the code of practice, unless this code of practice is changed. So at least we have the first criterion. But there are other criteria also. Can you think on any other criterion? I will wait here for a moment. Please email me. On your suggested criteria. Okay, anyways, I can say, so there could be some good criteria naturally when we make suggestions. Good criteria. Or bad criteria. Okay, I will bring you an example of bad criterion. Bad criterion is not sigma 1, not maximum stress is responsible for failure, but intermediate stress. Sigma 2 is equivalent to both, should be equivalent to both cases. But here, look, here there is sigma 2. Here sigma 2 is 0. We are comparing this state with this one. Yield. That means that this would say that because that is sigma 2 is 0, this never fails because 0 is always less than sigma yield. So actually we would arrive at a conclusion that it never breaks. So that is a bad criterion. Okay, please send me other examples of bad criteria. Okay, for example, of course, sigma 3 is equivalent, then it's also bad criterion. Sigma 2 should be the same, or intermediate stresses should be the same. That is a bad criterion. The same is smallest stresses should be the same, also is a bad criterion. Okay, so at least we will continue this topic. Now we are coming back to something that we had, hopefully we had in strength of materials. Please send me, if you had this, please inform me. If you had this material taught in strength of materials course. Okay, first of all, we take an element, and multi-axial stress is not only normal stresses, but also shear stresses. So we have this element, and pay attention, I will make some notations. That is x direction, this is y direction, that is z direction. So there are 6 faces. So this cube, there is this cube. So in here that is dx, that is dz, this is dx, this is dy. Now there are normal stresses, sigma in x direction, sigma in y direction, sigma in z direction. But there are also shear stresses. Now that is the shear stress, this shear stress. Pay attention, this face where this stress acts is perpendicular to this axis z. So then we put this z as a first index. It is directed in y direction, we call it therefore tau zy. Tau is a shear stress. Sigma is a normal stress. Normal stress. Tau, shear stress. Okay, then there is another stress here, shear stress, this one. So it acts in the same place. So therefore, I will here. Tau z, but direction is x. Tau z x. Then here also, on every face, there is a shear stress in y direction or z direction. Here, shear stress either in z direction or y direction. In total, we are ending up with the following stresses. Look, that is a table, okay, or matrix. Okay, sigma x, that is in x direction. Then, that is, look please here. Then there are taus that in y direction and z direction. So we write on this face, what happens on this face. Then we write what happens on that face. Tau in x direction, that is this one. Tau y, that is, this one is tau yx. Then sigma y, and then tau yz. Then in here, on this face, tau zx, that is this one. Then tau zy, that is this one, and sigma z. Okay, we can prove that, look please, if there is this is an element. Okay, so here let us consider this force. That is tau yz, and this is tau z this one is tau zy. Okay, so let us look from here. Then we will get, look please, tau yz, and that is tau zy. So then if I take the moment with respect to this point, okay, then moment should be equal to each, moment equals 0 naturally for equilibrium. We are getting the tau yz equals tau zy. So shear stresses with, when we change the indexes, the shear stresses are the same. So that means that this matrix is a symmetric matrix. This equals this guy equals this one, and this guy equals this one. Okay? Now, when we say stress, what does it mean, stress? Where does it act? Okay, so now we are reviewing this chapter 9. That is 9th edition, but also chapter is 9. That is called stress. That is plane stress transformation. I'm reviewing this in hope that this material was studied. However, in case that it was not studied, still you can understand everything according to my simplest possible explanations. Trust me, I'm spending extremely big amount of time in order my explanations to be made as simple as possible. They are not more simpler than possible, but they are extremely simple. Pay attention. I have to, because of preparedness or lack of preparedness of the students, I have to all the time review and go ahead, review and go ahead, review and go ahead. Okay? Now let us consider the plain, simpler case, plane stress. Why? Pay attention. Imagine in this element there is sigma x, sigma y, tau yx, which equals tau xy, because tau's on adjacent corners are equal to each other, if they meet, as it were, in this corner. Now, why I said I will not consider this case? Because the following. Our criterion was that maximum stress matters. The question is, if I took a cube and these are the stresses that act upon it, what happens if I will have to cut around this point, this cube in another direction, and consider this cube? What happens on that cube? Why I'm asking this question? What happens in this cube? What happens in that cube? Because I want to find the maximum stress. Maybe I made this cut and I have some stress, but maybe if I would have made this cut, the stress would be bigger. I don't want to overlook the biggest stress. So let me principle. I don't want to randomly overlook the biggest stress. Okay, then pay attention. If I'm cutting at some, that is an angle theta, at angle theta, then in this new situation, there will be sigma x prime, that is a new axis, x prime. This will be tau x prime y prime. In original system, there is sigma y, sigma x. Okay? And there is also this stresses, tau xy. Okay, then pay attention, strength, chapter 9 says that these stresses can be calculated from equilibrium of this element. Equilibrium. So we get sigma x prime equals sigma x plus sigma y, so that is tau xy, plus sigma x minus sigma y divided by 2 cosine 2 theta, that is this theta, plus sine tau xy sine 2 theta. And this new shear stress will be tau x prime y prime equals minus sigma x minus sigma y over 2. Here is cosine, but here is sine 2 theta plus 2 tau xy cosine 2 theta. How to obtain sigma y prime? So what is the sigma y prime? Actually, there is this element. So that is sigma x prime. So that is sigma y prime. So sigma y prime is nothing else but sigma x prime calculated at theta changed 90 degrees plus theta. Because between these two faces, there is 90 degrees. That is 90 degrees. So then I substitute here instead of theta, theta plus 90 degrees, I get sigma y prime. Equals sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 cosine 2 theta minus sine tau xy sine 2 theta. So that is, instead of plus I get minus, instead of plus I get minus. Now we will put some, okay, so pay attention. In original direction, I have sigma x and sigma y. In new direction, there is sigma x prime, sigma y prime. I'm looking where is stress bigger, because stress in biggest value of stress will be playing a big role. Definition, principal directions. Principal directions. Principal directions are directions such that tau x prime y prime equals 0. So that is the definition. If there is a direction where tau xy does not exist, then this direction is a principal direction. So principal directions cannot stand tau. They want tau to be 0, not present. That is our human's definition of principal directions. So it's very simple then. We write down tau x prime y prime equals minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta, and we equal it to 0. Then we divide it by cosine 2 theta. We get here tangents 2 theta. Tangents 2 theta principal equals then this tau. So I put this tau to the right-hand side will be minus. But minus divided by minus will be plus. So tau xy divided by sigma x minus sigma y divided by 2. Okay, so that is one consideration, principal directions. Then we are asking the following question that we were interested. Where are the maximum normal stresses? Okay, we differentiate sigma x prime to find this. Okay? Because at maximum, first derivative equals 0, or minimum. That is O maximum, so first derivative equals 0, or minimum. Also first derivative equals 0. So this sigma x prime d theta equals 0. So we have, I rewrote this formula. Sigma x prime equals sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. I differentiate. This first term will give me 0. Maybe I'm going too fast, so I will wait a minute. So we get this term, when we differentiate, is 0. Cosine 2 theta's first derivative is minus 2 times sine 2 theta. Sine 2 theta's first derivative is 2 times cosine 2 theta. This guy equals 0. But voila, pay attention, what we found, that this expression is nothing else but tau xy's expression, 2 times tau xy. Look, please. Let me show you this. Okay, that is tau xy, and that is a derivative of sigma x. So this derivative is 2 times this expression, because there is 2 here and 2 here. So that means that extremal normal stresses act in principal directions. So that means that, look please, there is some direction, we have to find it, okay, theta principle. So here there is max sigma extremum, and there is no tau. If there is sigma maximum, then there is no tau there. Okay? So expression was this. Look, please. Tangents to theta principal equals tau xy divided by some quantity. So then we can put it here, 2 theta principal. Here, opposite direction, opposite side is tau xy. Adjacent side is sigma x minus sigma y divided by 2. Then this one, hypotenuse, equals this one. Then I can get sine of this 2 theta p. Sine equals this divided by hypotenuse. Cosine 2t equals adjacent side divided by the hypotenuse. So I can get the sine 2 theta p, cosine 2 theta p. Then this we substitute back into formula for the stresses. Into here. Then we get sigma maximum minimum, that means extremum, sigma x plus sigma y over 2 plus minus sigma x minus sigma y over 2 squared plus tau xy squared. For example, just an example. we have this following element. That is sigma x equals this, sigma y equals this. That is tau. Tau, imagine, equals 400. So sigma x equals 1600. Sigma y equals 1000. How much is sigma max min? Equals sigma x plus sigma y. 1600 plus 1000 divided by 2 plus minus square root. Sigma x minus sigma y, 1600 minus 1000 divided by 2 squared plus 400 squared. So will be sigma max min equals 2600 divided by 2, 1300 plus minus 1600 minus 1000 is 600 divided by 2 is 300 plus 400 squared. So this is very simple. That is so-called, this is like Egyptian triangle. So then it equals 500. So this equals 1300 plus minus 500. So sigma maximum then equals 1800 and sigma minimum equals 800. Okay, that means that, look, please, original state is 1600 and 1000 and shear is 400. This will be like this. Somewhere will be 1800 and this will be 800 and there is no shear. So these are principal stresses. Okay, I just use this formula. These are neat formulas. Okay, in principal directions, tau is 0. That we understand. Now, what happens with maximum of shear stress? We can ask. We answer the following question. What is the maximum normal stress? Now we have a question. What is the maximum shear stress? Okay, we can just write down the expression for the shear stress and make proper differentiation. Are we done with this example? I just invented the number so that I'm getting an Egyptian triangle and I can calculate it very easily. I was just lazy. I did not want to put any numbers and then need to calculate square roots, so I did a shortcut. Any questions? We continue then. Maximum in plane shear stress. We may have said, come on, if maximum normal stress is most important, then why in the world I need maximum shear stress? We will need this later. We are making a good investment. So, okay, the formula of transformation is tau x prime y prime equals minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta. As I said, please tell me if you learned this transformation of stresses in plane stress, because that is very important. If you did not learn, I'm teaching now. But you did learn, if you did learn, then in the next semester, this part will be skipped by me. And I don't need to spend time on this. I could spend more time on other topics. So I differentiate expression for tau x prime y prime with respect to theta. We get, okay, sine 2 theta's derivative equals 2 times cosine 2 theta. Cosine 2 theta's first derivative equals minus 2 times sine 2 theta. So I get this one. Then I divide again by cosine 2 theta, I get tangents here. So tangents here equals this guy divided by this. Minus, because I transfer 1 to the right-hand side, so 1 minus will be staying. Minus sigma x minus sigma y over 2 divided by tau xy. So I wrote here tangents to theta shear. What is theta shear? That is a theta where shear is maximum. Before, we obtained tangents to theta principal. That is where shear is 0. Here, shear is maximum. Shear is 0. So I will write it down. Shear is max. Shear stress is extremum. Or takes extremum value. And here, shear stress is 0. Okay? Now we can calculate product of these two tangents. And we get tangents to theta shear times two tangents to theta principal equals this. Look, whatever is here in numerator, here is in denominator. Whatever is in denominator, here there is a numerator. Their product equals minus 1, because there is minus sign. So that means that if tangents are minus 1, that means that two angles, 2 theta shear and 2 theta principal, are orthogonal to each other. That is, you learned in analytical geometry, as well as in calculus. Or theta shear and theta principal are 45 degrees apart. How much is tau maximum? We are obtaining this formula. Sigma x minus sigma y over 2 squared plus tau xy squared. I'm waiting because when you are not sitting here, I'm tending to go further, faster, because there is no one to tell me, please, wait, professor. So now I have to exercise self-control and self-management. How did I obtain this formula? Okay. So we wrote tangents to theta shear on previous page equals minus sigma x minus sigma y over 2 divided by tau xy. From here we get 2 theta shear, and then we substitute into formula of transformation. Tau x prime y prime equals minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta. And then we will get this expression. How did we get this? Okay, this formula. Any questions? Maybe I will repeat what I said in the very, very beginning of the lecture, that we are left with one test and one more project that I will be assigning as soon as possible, means before or on April 9, because the second project you should submit by April 9, so I will assign probably on April 9 or April 10. And we will have 2 more weeks to submit it. Then one retake test. The data was given, I think the data of final test that was scheduled. We don't have a final test, we don't have a final exam. This course, professor has a right to not to have final exam. On the first day of the course, professor should announce the rules. These rules may include having no final exam. Why I canceled this final exam? Because extremely many students, research shows, are preparing to that final exam. They say, I will succeed in final exam, I'm smart, I'm a genius, I am outstanding, therefore I'm not going to do almost anything during the semester. Then they come and they fail. In order to prevent that failure, I decided not to have that test, but rather every time that you take a test, 1, 2, and 3, that is actually like final exam. You do a project, that is like final exam. You submit a homework, that is like final exam. So projects total is 30 credits, which is like 1.5 exams. Okay, here, tests in total give us 60% contribution, and project gives 30% contribution. So that means that projects give half the contribution of the tests. Yes, tests are very important. However, projects are not negligible. If student says, okay, I will do the test, I'm not going to do any projects, projects are a must. If student does not submit even one project, then he will not graduate from this course. He cannot get passing grade. Okay? So this allows actually that also in the test I put 40% of the test I put as a theoretical part so that you will learn the theoretical part. By the way, I have a couple of minutes left. During the test number 1, are you having a class? 3 more minutes. Okay, test 1. I did not write percentage of theoretical part, but I wrote then problem 1 40% and problem 2 also 40%. Then students should have decided that this theoretical part was 20%. However, I graded theoretical part because students do much better as 40%, and this 30%, and then 30%. So as a result, de facto, everyone got more grade, not everyone, almost everyone got a better grade than he could have obtained with this, so that is 20. However, some students could do better with this one. So what I will do, I will check every student by which grading he or she gets better grade. And I will adopt for the students that grading. So that some students' gradings will be improving even further. They already improved by this grading. So that was my misprint. I can say my mistake because I mistakenly did not write this. However, this was justified because each of you spent at least 30 minutes, I asked. No one did it less than 30 minutes. So 30 minutes over 80 minutes is 37.5%, which is very close to 40% that I'm assigning. But anyways, I will make correction of the grades of couple of students. There will be